All right, so we are on Mod 12 and we're talking about different types of protocols that are aren't real large, or really big, but very important, and networks couldn't run without them. So this is the topics that we'll be talking about. We're going to be talking about address binding using ARP and DHCP protocols, error reporting using ICMP, bootstrapping, meaning when the computer just turns on, how does it get its information? So that's BOOTP. And then address translation, which the protocol for that is NAT, network address translation. And that's going for public to private IP addresses. So all of these handle a small piece of the big network system, but they're all also very important. So let's start off with ARP, Address Resolution Protocol. So we all know that in order for a device to be connected to the network, it needs a network interface card or a NIC, right? And so it could be a wired NIC where you plug in an Ethernet cable. It could be a wireless NIC, right, that sends out the signal. These NICs over here are kind of portable. They kind of plug into the side of your laptop also. So there's different types of NICs, and a lot of computers, especially laptops, have more than one. They might have a wired NIC and a wireless NIC associated with it. But every device has to have a network interface card in order to connect to the internet or connect to the network, right? And so what ARP does is it translates the IP address to the MAC address. And the MAC address is basically the serial number for that NIC card. We'll talk more about that here in a second. So, but you can think of the MAC address, it's hard-coded into the network card, and it's kind of used as kind of the serial number that makes everything unique. So, in order for ARP to work, though, it only is available inside the same network or the same LAN. ARP does not pass through a router and does not look at other networks that are connected to it. So if A wanted to know B's MAC address, it could find that out because they're on the same network. But if A wanted to find F's MAC address, it could not. It would have to use a different process. Okay. So here's kind of an example of how it would work. You might want to kind of pause the video as I explain it and to kind of look at the numbers a little more closely. But first thing I'll point out is the source IP address and the destination IP address does not change through this process. So X is sending an email or a message to Y. So the source IP address, 30, is always the same, and the destination IP address, 192.4, is always the same. What does change, though, is the MAC address. So when X wants to send this out, all it sees is, or the next hop it knows about, is this first router. So you can see that the source MAC address is the host MAC address, 5C, but the destination MAC address is the inside MAC address or NIC card of the first router, 1A. Then it leaves, and as it leaves this router, you'll notice that the source MAC address changes to the outside NIC card MAC 6D, right? The destination MAC address is of that of the next router or the next hop, 2B. Then as it passes through that router onto the next network, the source MAC address, 4C, right? And it's sending it to the next router. That next router's MAC address is 03. So you can see that here. And then finally at the end, the inside, so this is the final network that we're getting to. So the inside MAC address NIC card of that last router, 6F, right? And then the destination MAC address is that of the Y computer, right? 4D. So again, pause it, kind of walk that through, make sure you understand that process. The IP addresses don't change, but the MACs do as they go from one hop to the next. When a computer wants to find out the MAC address of another device, right, it'll send out a broadcast, and because it doesn't know who it is or where it is. So here in this situation, computer B wants to find out the MAC address of computer C. So it sends out a broadcast. A and D ignore it. They're like, I don't know. But C says, hey, I'm IP address C. Here's my MAC address. And C responds directly to B. And now B and C know each other's MAC address. That's the way that works. And again, it does not switch, it does not pass through to other subnets. It's only contained within that network or within that subnet. And so with this kind of slide it's talking about is most of the examples, most of the time, ARP uses Ethernet. And with Ethernet, it uses the MAC address, right? A 48-bit long MAC address. So most of the time when we're talking about ARP, we're talking about Ethernet and NIC MAC addresses. But just kind of full disclosure here, right? The way ARP is set up is it is flexible enough that if other hardware, if other situations develop that have a code or a quote-unquote MAC address that's a different length than 48 bits, then ARP is able to handle that. But again, that's really not used much, especially kind of where we are in the learning process. Okay, so this is what a header looks like for a ARP message. This is the information and how big that each field is within that header. And it says here, and again, most of the time we are binding an IP address to a MAC address. This up here says an arbitrary high-level address, which means any type of IP address, to an arbitrary hardware address, meaning it doesn't have to be a NIC card. It could be something else. But again, for what we're dealing with, we're talking about IP addresses and MAC addresses on the NIC card. So again, this is a breakdown of what the ARP header looks like. And when we're talking about hardware, we're talking about MAC addresses. If we're talking about a protocol address, we're talking about an IP address. Okay. You can kind of glance through and read through kind of what each field does. I just want to emphasize this operation field, because when you send an ARP message, or when you have an ARP message, the question is it a request for what to know what somebody else's MAC address is, or is it a response from that other computer saying, hey, this is my MAC address? So that operation field states whether it's a request, an ARP request, or an ARP response. Okay. So, and in this slide, what we're looking at is how does a request ARP message fill up all of these sections of the header if it doesn't know all the information. So when B sends an ARP request wanting to know what C's MAC address is, it doesn't know what his MAC address is. So in this target hardware section, it'll put in all zeros, saying, hey, these all zeros, I'm just filling up this space so the router and everybody else kind of knows what the process is, knows where to look and what the information is. I'm just putting in zeros because I don't, for now, as holders, is a holding spot, because I don't know what the destination MAC address or hardware address is at this time. Okay. Then we talk about encapsulations. We've talked about this a few times. So this ARP message is no different. As it's moved down into the data link layer and onto the physical layer, right? that ARP message, it gets encapsulated into a frame, and the ARP message becomes the payload. The frame header is added, and of course the CRC, the cyclical redundancy check for error checking, is added also. So that's encapsulation. And when that frame is sent, right, and they have to look at it to know what to do with that particular packet, here in the protocol address type is where we say, hey, this is an ARP message, right? It's not a UDP, it's not a ping, it's not anything, it's an ARP message. And then in this and then the type for that is type number is 806. So they put 806 in there. So now all the devices know, hey, this is an ARP message. I will kind of throw this in there, this 0x. Hopefully you remember what that means. That means it's hexadecimal. So this 806 number is actually a hex number because of the 0x in front of it, right? Then again, the operation field that we talk about is here, and that says whether it's a request or response ARP message. So technically, right, ARP belongs to the second layer of the networking model. So it sometimes is referred to as the network interface layer, right? So here's the ARP protocol there. And that's on the 5-layer method or 5-layer model that we're using here through UC. But sometimes if we're talking about the 7-layer layer, it might refer to as the data link layer. So I mention that because the data link layer and the network interface layer are often used interchangeably. But in either case, they're the second layer of the networking model. Okay. So let's move on. So when a device, a computer or say wants to send an email out to another computer, and it doesn't know what that MAC address is, it'll send out an ARP request. Well, when you send an ARP request, right? So here, this computer is sending out an ARP request, then it gets the response, and then it sends the packet. So that's 3 different exchanges. Well, when you send an email or a file or whatever it is you're sending, typically it's thousands of packets you're sending. And if each packet has to come up with an ARP request and an ARP response before it could send the datagram, that is so much more traffic on the network that we need to deal with. So to kind of get around that, the first packet that is sent sends an ARP request, gets the response, gets the MAC address, and then the computer or the router, depending on what it is, right, will then save that information. It saves the MAC address of the next hop into a cache. And a cache, you can think of a cache as or a table, right? We've talked about forwarding tables in the past. So ARP kind of caches or has a small little forwarding table for MAC addresses that it uses. It is a small one because when it runs out of space, the oldest MAC address in there, the oldest entry in the table is kind of dropped off. And next time you have to send something, it has to do another ARP request and find that MAC address again and repeats it. This is what an ARP table looks like, or an ARP cache looks like. So you can see dynamic here and static. Here's the IP address, and here's the physical or the MAC address. So if it's a dynamic IP address, and we're going to be talking about this in a few slides, that means this IP address can change and will change over time. If it's static, that means these IP addresses will not change. They're hard-coded in, they're there permanently. Typically, servers use static IP addresses, where hosts or devices will use dynamic IP addresses. So go ahead and pause the video, pull up the command prompt, and type in ARP space -A and take a look at your cache real fast just to check it out. Right? So when we're talking about ARP, right? ARP works on the network interface layer, but really it also interacts with the internet layer. So ARP is kind of a gray area protocol that helps connect the internet layer, which works with IP addresses, and the network interfaces will work with MAC addresses. It resolves or helps the packet transition from the internet layer to the network interface layer. Okay. Yeah. All right, so let's move on. That was ARP. Now let's move on to a different protocol called ICMP, Internet Control Message Protocol. And the purpose of this packet and this protocol is kind of does two things. It detects errors and it retrieves information. So some of the errors that it'll detect is the checksum. So if you recall, when a packet's sent, they do a little algorithm, a little math to say, hey, when it reaches the destination, this checksum should be this number. And if it's not, we know it's that packet didn't make it there without being corrupted. And or it looks at the time to live field, which we've talked about this, right? So after it goes through so many hops, if it reaches the end of the hop limit and is destroyed, then the ICMP packet pops in to let them know that, hey, this packet did not make it. And so here are the different types of messages that an ICMP packet can handle. The echo are the ping packets. We've messed with ping. And we've also dealt with trace route. So these are retrieving information. The time to live, the destination is unreachable. Some of these other ones, they have to do with error detection, right? Now, again, I just want to kind of put things in perspective. We're talking about an ICM packet, right, that reports errors and retrieves information. We are not talking about an ARP packet or a TCP or UDP packet or even a GET packet. If you remember a GET packet, you will see on Wireshark when you're collecting packets over a network where you're looking for a web page, right? That's the initial request to find a web page. So these are all different types of datagrams or packets that you will see when you use Wireshark, right? So here again, this is kind of repeating the information, right? The M in the ICMP stands for message. So it's just telling or reporting something. And typically it either reports errors or retains information. Now here's an encapsulation. It works the exact same way as all the other packets. As it comes down through the different layers of the network, each layer adds a header, and that header becomes the payload of the next layer as another header is added, and that becomes the payload as another header is added. So, that's how encapsulation works, right? And again, ICMP is a layer 3 protocol, not a layer 2 protocol, right? It's technically a layer 3 protocol. Okay. In this slide, we're just, again, kind of saying the same thing. As it says, as it sends information out, right, the ICMP datagram gets no special treatment. It's just like any other packet floating around the internet. The only exception is if by chance that ICMP datagram gets corrupt, right, and doesn't make it to its destination, no error message is sent, right? it is the error message. So that's kind of the only really difference there. Otherwise, it works like any other datagram. On kind of a side note, kind of fun little topic here that you might be interested in. The ping, which again is an ICMP message, ping message is often used in denial of service attacks. So a DOS attack is when a server, a computer or a server, is just bombarded with packets of information until it gets overwhelmed and then the server shuts down. So maybe you're trying to shut down a website. So this bad actor here gets on a whole bunch of bots and a whole bunch of computers around the internet and sends out thousands of ping messages to that one server until that server kind of shuts down. So it's used. So the ICMP ping packet is used for that. Although other protocols could also be used in denial of service attacks, but the ping message is probably the most popular, most widely used method. Okay, we're going to stop here and switch up. Up until now, we've been talking about IP version 4. Just want to take one slide here and talk about IP version 6 because it does work a little bit different. Version 6 does not use ARP at all. It uses a similar type of protocol or similar type of system called neighbor discovery. And neighbor discovery kind of reaches out to other devices and other routers that it's connected to and kind of gets a list of the MAC addresses around them. So again, IP6 does not use ARP. It uses neighbor discovery. Let's go back to IP version 4. And when we are talking about configuring or setting up a router for the first time, a human being, the network administrator, has to set some things up manually. So the first thing, in order to get a router up and running, a network admin has to do is it has to give it an IP address for every connection. So typically there are at least 2 NIC cards on every router, an internal one for the private IP address and an external one for the public. It could have more depending on how many routers or networks it's connected to. Then the network admin has to decide what protocols to run, right? Well, we need ARP and we need, spanning tree protocol, and we might need a DHCP relay protocol, and whatever it is, it has to decide what protocols are needed on that particular router, right? Then it gives initial values for the routing table, and it could be just as simple as putting in the default hop, right? But it'll put in a couple values in the routing table until it gets started, right? Then the network admin saves it and then loads the router and puts it on the internet or on the network. Once the router is up and running, all this stuff is done automatically, right? So once it's running, assuming it's set up properly, everything from there is automatic, and the network admin has very little management of it. So that's starting up a router. If we're starting up a host, which is typically a computer, right, a desktop or a laptop or whatever, it uses a process called bootstrapping. Most of the bootstrapping techniques are used by or is taken care of by DHCP, which we'll talk about here in a second, okay? But when a host is starting up for the first time, it uses this bootstrapping process, which kind of has 2 steps to it. The first step kind of loads some automatic default settings, right, that every computer has to have and know. Then the second step has to reach out that computer, the device, has to find out what its IP address is and a subnet mask is, what is the IP address for the DNS server and the default gateway, and some other information. This is the information that the DHCP server will hand out to the different devices. And so that's what DHCP does. It's Dynamic Host Configuration Protocol. So when a computer starts up or connects to the network for the first time, or maybe for the first time in a while, right? It says, hey, Mr. Network, I need an IP address. Can you give me one? And then the DHCP server will say, sure, here, use this IP address. And that's the kind of the conversation that the DHCP server does in that bootstrap process. And why do we need a DHCP server? Why can't we just hard code an IP address into every address or every computer on the network? Well, think of it this way. Your parent, your mom comes to school and she wants to connect to the network for whatever reason. So she kind of gets in there, and our DHCP client gives her an IP address that she can use and connect to the network. But then your mom leaves, and she might not be back for a day, a week, a month, or maybe never comes back and has to connect to the network. If that's the case, then that IP address that was given to her is no longer available for anybody else at school. So the DHCP server, what it does is it will take that IP address back. So when it gives an IP address out, it's really only loaning or leasing that IP address for a short period of time. That way, we can use a pool of IP addresses, so maybe 100 different IP addresses. But as people come in and out of school asking to connect to the network, well, that might be hundreds of people. So we can serve and connect hundreds of people with just a limited number of IP addresses if we use DHCP. And like I said, that IP address is not given, it's loaned or leased to that individual device. And it's leased for a specific period of time. So in this example here I have, right, I went and I obtained an IP address at 11 a.m. in the morning, right? Later that night, right, 7 hours later at 6 o'clock, that lease will expire. In the computer, the DHCP server will take that IP address back. But I don't need it at that point, right? I used it during the day. I don't need it at night because I'm at home. Tomorrow when I come in and I log in to the network again, I will get a new or a different IP address on it. Most IP addresses these days are given out through DHCP. So go ahead and pause the video for a second. Go to your command prompt. Type in ipconfig /all and see when your IP address is going to expire. But don't panic, because if you're still using your computer and it expires, it will give you another one or extend the lease on this one, depending on how it's set up. Okay. So it kind of works like this. When a client gets onto the network, the first thing it does is says, hey, I'm looking for the DHCP server. Anybody know what that is? And the DHCP server responds and says, oh yeah, that's me. Here's my IP address and my MAC address if you need to get a hold of me. Then the client responds, yeah, actually I do. Can you give me an IP address, please? And the DHCP server responds, sure, you can use this IP address. So this communication back and forth happens, obviously very quickly, but that's the process of how a client will get an IP address when it's new on the network, right? And then, of course, once that client learns the IP address of the DHCP server, then it caches it, it saves it, So the next time it gets to that network, it can go right to it. It doesn't have to do these first two steps. It just says, "Hey, give me an IP address," and it gives it to them. What happens though if an IP address needs to go through a router? So if you recall, we talked about private IP addresses are not routable, meaning private IP addresses cannot pass through a router. Well, what happens, if we look up here, here's a network with 4 different subnets. And these 4 different subnets use routers to connect them and eventually to the server. Well, remember, a private IP address it can pass through a switch, but it cannot pass through a router. Unless, of course, it has a special service turned on called a relay agent. So if this router, the network administrator says, "Hey, Mr. Router, you are now a DHCP relay agent," what that says is when a client with a private IP address is trying to reach a DHCP server through a router, the router will go, "Oh yeah, I recognize you are looking for the DHCP server, even though you are a private IP address, I'm going to pass you through anyway." So that's what relay agents do. It allows a private IP address to pass through it in order and only in order to get to a DHCP server. Okay? And you have to have at least one relay agent on each network, assuming that it has a router on it, right? Okay. So why do network administrators use this relay agent, right? What they could do is they could have a DHCP server on each one of these subnets, and that way not having to worry about it routing through a router. The problem with that is every time you add a server, that's more work for the network admin. So we use relay agents for 2 reasons. The first one is it's a heck of a lot easier for the network admin to manage the IP addresses if they're all in one location, right? And the lease policies and everything's together. So that makes it so much easier. The second reason is because routers these days all have that relay service built into it. So it's really easy for the network admin to just kind of, turn that service on in the router. It's low work, it's easy work, and it's done quickly. So that's why we use those relay agents these days. Let's pause briefly and switch gears to IP version 6. So IP version 6 really does not use DHCP because version 6 can create its own IP address. And part of that process of creating its own IP address is using its own MAC address as part of that IP address. So that version 6, remember, IP addresses are written in hex. They're a lot longer. They have more information in them. So DHCP is not used with version 6. Okay? But let's go back now to IP version 4. And now we're talking about another protocol called Network Address Translation, or NAT. And again, I just want to kind of up here make sure we understand the difference. We're talking about NAT, which is going to associate a private IP address with a public IP address. Not to be confused with ARP, which resolves an IP address with a MAC address, or a DNS, which resolves an IP address with a domain name, a full qualified domain name like, stxavier.org or whatever, right? So we're talking about NAT, and the private IP addresses are used internally The global or public IP address is what's seen from the outside. So in this example here, this shows you kind of how that process works. My source IP address and my destination IP address are always the same, or the destination IP is always the same. Once that source IP address goes through the router, right, and comes out the other side, then the source IP address becomes the external IP address of the router. So this is the public or globally recognized one. Everyone out here in the world that is looking at this organization sees this as its IP address. Even though on the inside, it could have 100 different hosts and they all have different IP addresses. But it doesn't matter because the rest of the world just looks at this outside one. Then NAT will translate that outside IP address back into the private IP address for the particular host that it needs to attend. So again, coming back, the destination IP address here coming back from the server is the external or global or public IP address. Once it gets through, NAT translates the destination IP address to the local. Okay. Again, this is just reviews what I just said, right? From the outside world, it sees one IP address, the public one. From the inside of the network, it sees a different IP address on that router. We've talked about private IP addresses and different classes of IP addresses. So every class A, Class B, and Class C, has a block of addresses that are reserved for private networks, right? For inside of LANs. You'll see 192.168 a lot. That's probably the most common, although you will see some of these other ones from time to time. Again, just as a side note, who made the decision here? Well, that international organization called IETF made the decision that these blocks would be considered private. And again, this is kind of the same information, kind of repeating here. You got the private internal and the public external IP addresses, right? Again, this is a visual demonstration of that. So kind of color-coded the numbers here. So when computer A wants to send something to computer B here, right? Notice the destination IP address doesn't change, but the source IP address does. Goes from public and then switches over to the global once it goes through the NAT. And then the same thing coming back. Takes that global and switches it back to the private. So again, you might want to pause the video, make sure you understand how those numbers work. Okay, so we went through a lot of information right here. Quick summary. Remember, ICMP works at the network layer. ARP is kind of that gray area, right? It works at the network layer and the data link layer, right? Because it maps IP addresses to MAC addresses. So it kind of has a foot on straddling both sides of that. We talked about IP version 6 and how it's a little bit different. There's no ARP or no DHCP with IP version 6, and everything is pretty much done automatically. We talked about the DHCP server, which just kind of requests an IP address when it joins a network. And it not only gets an IP address, but also gets subnet mask, default gateway, DNS address, other information along with it. Then we talked about NAT, which again resolves the public IP address with the private IP address. Okay, very good. So it's a lot of information. Good luck with you. If you have any questions, of course, as always, make sure you see me.